Yeah, hello, ladies and gentlemen. Welcome to this last lecture on 3D coordinate systems. This time we will talk about outlier detection. Up to now we assumed that all the data are clean, in the sense that they are only disturbed by random errors, small random errors which we can describe by approximately by a Gaussian distribution. And we use this information for the estimation and also for the evaluation. But of course, all these results only hold if there are no gross errors, blunders, outliers, or how you call them. And today we will discuss how we solve this problem with outlier detection in our context, and we will see that this can be generalized to quite a number of very interesting problems. So let's start with an example. We have here 7 points in 2D. And we now translate them into the second system. So we have the same points here. You see the configuration. And now we rotate and scale it. So it's turned to the right and upscaled. And now we introduce 2 outliers. So let's do it once more. So you see that 2 points, this one and this one, are shifted by quite some amount. So we get now this configuration. Now forget what we did just now, and the question is, we now assume that we have given these 7 points in the first system and these 7 points in the second system. They don't look like to be the same configuration. We know that it is nearly so, but at the first instance we don't see this. And the question is, if you would see these 2 configurations, would you know which points are outliers? Whether there's 1 outlier, 2 outliers, 3 outliers. So this is exactly our problem, which we want to solve. So of course, we know from the generation process that it is 5 and 6, but this is exactly what we want to find out by some automatic procedure. So let's start. I give you the topics of this lecture. The first, we will talk about what outliers are, what is the notion of outliers within our estimation procedures. We will look into the complexity of this problem. And then we will have a look at 2 methods which are called complete search, and the other one is random sample consensus. So what are outliers? So let's start from the beginning with the Gauss-Markov model, for which we used for describing our problem. So we have here our observations. These are the measured coordinates in our transformed systems in our context of similarity transformation. So these are fixed values, and we assume they are a sample of some random vector L, which is distributed following a normal distribution, which has a mean, which depends on unknown parameters. We know the function f, so we know the functional relationship between x and L. And some covariance matrix which describes the noise generating process for getting the random variables L. Now, if there are errors in the data or errors in the model, we will not be able to distinguish these 2. So if there's a discrepancy, so for instance, our estimated variance factor doesn't come out with 1, not with 1.1, but with 5. We have no idea what the reason might be. So it could be outliers in the observations, but it also could be that the model is just wrong. What does that mean? So the model might say it's a similarity, but in reality it's a pure rotation. So we might have too few parameters, or we may have too many parameters, or we just model the similarity in a wrong way. The second is the covariance matrix may be totally wrong. So we just could say the observations may be accurate to 1 centimeter, but in reality they are 5 centimeters. So then, of course, our estimated sigma naught will be 5. We could also have neglected correlations, which we discussed last time. So there are, and we will not get the correct value for the variance factor. And of course, we assume here that the data are normally distributed, which of course needs not be the case. Actually, the reality will not follow a normal distribution. So the normal distribution is a model which we use for our purpose and which in many cases is quite fine. But in reality, there may be big deviations. And for instance, a certain percentage of the data are not within a small range, let's say plus minus 3 sigma, but quite outside this range. And then that means we have a distribution which is not a normal distribution. So we will not be able to distinguish between the errors in our observed values and this model which we have written down here. So that's the first thing. So we have to be careful when we talk about outliers. We talk about errors in the observed values. So these errors in the observed values may be, and this is a classical classification, random. That means we only have small random perturbations. We hope that these random perturbations are covered by the stochastical model up to now. And we just saw that there may be systematic errors, so we may have the wrong number of parameters or we have neglected covariance measures. So it may be that these errors are not distinguishable among each other. So if you have not enough parameters or you have neglected covariances, you may not be able to distinguish these two types of errors or even from random errors. And of course, everything else we would say are blunders or outliers, so we are not able to specify this in a simple way. And in practice, these are mostly identification errors, numbering errors. Like in our case, we just measured the wrong point. So, and these outliers we also could distinguish. They may be very small, so they may be even smaller than we can detect them, or they may be hardly detectable. They may be large, but still not detectable because our configuration is not good enough. They may be medium-sized, so they clearly show in the residuals, for instance, and they do not severely distort the estimate, but because the residuals are very large, we see that there must be some outliers. And there may be outliers which are very large. They certainly heavily distort the estimate if we really get an estimate. So it might be that even we don't get conversions in our process because of large outliers. So this is a classification, and the bad thing is that outliers are like bad people. There may be a few ones, but there may be several ones, many ones. So seldom, that means let's see, we have less than 1 per mil, or we have them often, let's say more than 10%, more than 50%, 90%. And the bad thing is, if they are isolated, you have this situation. If there are groups of them, they may be separate, so like this, but they also may mimic a good result. So if you want to find straight lines here, you find, so this triple is shifted here, but it also may be that this corresponds to this one, and these are outliers. So it's not very clear that if you have outliers and they are not rare, then the outliers may mimic a good result. Okay, let's have a look at the complexity of the problem. So in general, we have I entities, observations or points in the left and the right coordinate system. And each of those points or correspondences may be good or bad, may be inlier or outlier. That means we have for each 2 options. So for I entities, we have 2 power I options. So that means we have exponentially many of these alternatives. So let's assume you have 10 points and you want to find a straight line. then you have 2.10 alternatives that these points are correct or incorrect. So there are principally two types of approaches, and they differ significantly. One is to say, I search for the outliers or for the inliers. So you have a discrete problem. So we want to find that group of points which actually are inliers. And then we can use those inliers for the estimation. That's a discrete problem. Or we could modify our estimation procedure that it is insensitive to deviations, to violations of the model assumption. So if you have a Gaussian distribution for 99% of the data and a very flat distribution for 1%, then the distribution is off and you may be able to make some type of maximum likelihood estimation for this case. And if you have done this estimation, then of course you can make a decision from the residuals, let's say, whether certain points are inliers or outliers. Unfortunately, many real solutions to find outliers mix these two in some way. So the boundaries between these methods is a little bit blurry. So the idea of search would be, say, I take a minimal subset of the observations. So in our case of a similarity transformation in 3D, we would need at least 3 points to be able to determine the similarity. And then we take this similarity transformation and check whether this transformation is consistent with the other data. For instance, using the sum of squares of residuals. Of course, the problem is, how do we select such a subset? We can do it systematically, or we could do it randomly, or we could do it in a way which you invent. And of course, if there are many trials, does the sequence of the trials make a difference? So there are quite some problems if you do this in a discrete way. And if you perform a robust estimation, where the optimization function guarantees that the result is insensitive to errors in the model, I will not talk about this topic in more detail, then you get an estimate and then you can identify the outliers. And still you have the problem, how do you identify the outliers then? You can be conservative and be very strict, and then you can do a maximum likelihood estimation with these guaranteed inliers, and then you might look back and add some other points. So there are many strategies which are in this class. Now, let's lean back and ask how many points of 100 points, let's say, can be outliers without that the system, the outlier detection system, breaks down. This is what is called in statistics the breakdown point of an estimator. So the breakdown point of an estimator is the percentage of outlying observations which may allow the estimator to give arbitrary wrong results. And of course it's clear that if the maximum, if we have more than 50% outliers, those outliers could put them together in a group and say, hey, I'm the correct one. So they may mimic a good result, so the breakdown point certainly will not be larger than 50%. So let's make an example. Take the arithmetic mean of I points. Now let's assume we have one outlier. The outlier may be very large. And then of course it's clear that the mean, the arithmetic mean, will be arbitrarily bad. That means the breakdown point of this estimator is 0% because it doesn't allow any outliers. And unfortunately, all least squares estimates have a breakdown point of 0. So you always can just add one bad point, one bad observation, and you can make the result arbitrarily wrong. Let's take the median of the I points. So you sort all these data and take the middle one. And then, of course, if the majority of the data is good, then you will hit a good point. And take this as the estimate. This is fine. That means you have an estimator for the mean, which is not the arithmetic mean, but the median, which has a breakdown point of nearly 50%, which is an indication that there are estimators. The median is, so to say, another estimator, which is insensitive to deviations in the model assumptions. So this is an indication that such estimators exist. Now, of course, you would like to know whether least squares estimation may be useful for finding outliers. We have just argued that this is not the case. So let's take these two point clouds, left and right, as we discussed it in the previous slide. So if it makes the estimation of this planar similarity, we will get those residuals. Okay? We see that the residuals are really large, partly larger than the diameter of these points. The largest residual is at this point. This is point number 7. But this is not a wrong point. It's a good point. These two are the bad points. So even with this simple example, you see that the least squares residuals are not useful for finding outliers. If you have large outliers or if you have many outliers. If you have only one outlier, there are methods which can solve this problem, but this is not always very useful. So let's forget least squares estimation for finding outliers. And let's look at methods for solving the outlier problem. There are a lot of different conditions under which you can design such a procedure. And therefore there are many methods for finding outliers. So it depends on preconditions. So are there approximate values for the estimate available? Does there exist a direct solution for the problem? So the second question is the number of observations large or small? Maybe better if you have many observations, because then you have more possibilities to identify the wrong observations. The configuration may be homogeneous, so the points may be distributed more or less evenly, or they may be distributed very unevenly, so this may have an effect. Then, of course, the error rate has an effect. So if you have only 1 per mil of the data are outliers, then of course there may be more simple and more efficient methods than if we have an error rate of 40% or so. And then, of course, we have this problem, how many unknown parameters you have. If you have only 1 parameter, like in the mean, or only 7 parameters, like in the similarity, you can imagine that things are not so complicated. But if you have an estimation process with, let's say, 1,000 parameters, things may be very complicated. And it may be even not possible to use certain techniques. And of course, the methods depend whether there exist large outliers or there are only medium or small outliers. This makes an effect on which method you might use or design. So there are a lot of these methods which I don't want to sketch. I only want to show you 2 algorithms. And we make the following assumptions. We assume there is a direct solution for the parameters from a minimal set of observations. So in our case of the spatial similarity, we need 3 points. In the 2D case, we need 2 points. The number of observations may be medium, let's say only 2 times the number of observations, unknowns, let's say 7 points or so. Up to very large numbers, let's say 10 times or 100 times or 1,000 times the number of unknowns. The configuration, we don't make any restrictions on this, so it may be inhomogeneous. We assume that the error rate may be high, possibly, and we will see that this is possible under certain conditions, possibly above 50%. And we assume that the parameters, number of parameters is small, let's say below a dozen, and there exist large outliers. So this is, so to say, the boundary conditions where these two methods may work, or are intended to work. We will see that there is a possibility to distinguish these two algorithms, which I show you. Most algorithms which you program are deterministic algorithms. That means if you have a certain input, you have a fixed output for this input. Let's assume you have an algorithm which has a random number generator in it. Then, of course, the result will depend on the chosen random numbers. Then you have what is called a stochastic algorithm. And we will see that the second algorithm, which I show you, is a stochastic algorithm, which is very efficient. But unfortunately, because you have such a stochasticity in the algorithm, there is no solution guaranteed with 100%. So let's start with the first algorithm. That's complete search. So the idea is the following. For all possible configurations of inliers and outliers, we determine the solution and some evaluation function. And then we choose the best configuration. So if you have 10 points and you want to fit a line, you take one configuration, let's say 1, 2, 7 is an outlier, and the others are inliers. Then you estimate, makes the maximum likelihood estimation for the fitting line. You look for the residuals, and this is your evaluation function. And then you do this for all combinations and choose the best configuration. What we do in the following is to describe the configuration by a binary vector, which has the length of all these points. So if you have 10 points, it will be a 10 vector with zeros or 1, and if it is a 0, it's an outlier, and if it is a 1, it's an inlier. So how many trials do we need to go through if we do complete search? Of course, we have 2 power I possibilities to have good and bad points, but we would, in a case of a 2D line, we would not start to work with all points bad and all points except 1 not bad is also not good, and with 2 good points only we are not able to actually check whether these 2 points from the residuals are good. So we start with 3 points, and that means we have to exclude from these 2 power I these number of cases which we don't actually follow. The same holds, of course, in 3D, where we have to start with 4 points, 4 good points, in order to be able to take the residuals for evaluation. So in altogether we get k solutions with 3 or 4 to I good points. And for each we have to evaluate whether this is a good or bad sample. Altogether, if we neglect these 2 terms compared with the 2 power I, it's small, the number of trials is going up exponentially with the number of points. So how do we evaluate? The most easy way is to take the estimated variance factor for the inliers. So if delta is 1, we take the weighted squared residual of that point and sum over all the good points, and then we take the number of good points and subtract the number of parameters which we want to take. And you see the delta just is a decision variable which says whether the residual is smaller than a factor c, critical value, multiplied with the standard deviation, and c is usually in the range of 2 to 4. Now the bad thing is that if we have a small number of points, it may be that they lead to a very small variance factor. That means the number of outliers which actually are there is not counted. So we could also, instead of this variance factor alone, take an additional constant penalty for each outlier. So if we have a good point, we take this sum as here up here, and if it is an outlier, we add a constant c square, and that means for all outliers together we have to add c square multiplied with the number of outliers. This numerator can also be written in the following way by summing over all observations equally. So we take the minimum of the weighted residual square and this critical factor c square and take the minimum of those two. So this shows that the number of good points should be large in order to get the whole numerator small, which is fine. We will later see that this optimization function can also be used in a different way in terms of a maximum likelihood type estimation. So this is the first method, and it has the advantage that we can be sure that if we get the best solution, what is possible, because we have looked for all combinations. The disadvantage, of course, is that we have 2 power I configurations, which is fine for 10, which might be fine for 12 or 14, but certainly not for 20 or even larger, because then the number of alternatives which we have to check is just too large. So there is another method. Now let's assume the breakdown point of our method can be not larger than a half. That means let's assume that the percentage of outliers is smaller than a half. Let's assume this. That means the probability of choosing a sample of S inliers is the following. So we take the probability for choosing an inlier, which is 1 minus E epsilon. And then this holds for all the S samples, let's say 3 points in our case of the spatial similarity. That means we have a half power S, which is an eighth. That means if we have trials, let's say 20, it's very likely that we hit a good triple. And this is exactly the idea which has been proposed by Fischler and Bolles in '81, and they called their method random sample consensus. Why? Because they chose a triplet, or generally a minimal sample, and do this a certain number of times, only a limited number of times, small number of times, and then use the result and look whether the others are in consensus with the transformation which you get from the minimum sample. So we randomly choose a large enough number, t for trials, of samples of size S. So let's say t is 20 or 50 or 100, and S in our case of similarity would be 3, sufficient to determine the parameters. So this is guaranteed now, to hit a good triplet with high probability. So we would like to have that the sampling leads to a good result with a high probability. You see, we require a high probability, not 100% certainty. Otherwise, if we would have 100% certainty, we would have to very large sample, or even all samples which we just discussed before. So we want to only have a guarantee which is high, let's say 99% or 99.9%, etc. And as soon as we have such a sample, let's say of 3 points, we use the other I minus S points for checking for consensus. So this is the principal idea of Ransack. And you will find a lot of papers if you Google Ransack, and you can make yourself informed by looking at these papers. So let's sketch an algorithm for the spatial similarity which uses this principle of Ransack. So we start with having the data, which are the pairs of the points in the given and the observed system. We have, let's assume we have the standard deviations of these points, and we have I points altogether. So this is the data. We assume a certain outlier rate, which we later need for checking. So if there are more than epsilon residuals larger than the critical value, we of course would say the triplet is not good. And then we have to specify the number of trials. We will come to back how we do this later. So this is, so to say, the input. And then we iterate for each trial. We choose a random set, ST, of S points. That means we have here a set ST of 3 points. And determine the parameters, the 7 parameters of the similarity for this set. And then we determine a consistency measure, CT, depending on these parameters and the rest of all the points. And then we choose that set, that trial, where the consistency measure is smallest. Okay, some comments. The variance of data we need for determining the consistency. So if you compare the residuals with a certain threshold, you need to know how precise your measurements are. So this is the ideal case where you know this. If you don't know it, there exist methods to estimate the variance. I will make a comment to this later. The second is the number of trials. We can relate the number of trials which we need at least to the required probability of success. So it, of course, is clear that we need a certain number of trials for 99% success and a larger number of trials if we have require 99.9% success. This relation we will look into more in detail. Then we need to determine the parameters. That means we need to have a direct solution. I will show you one, which is quite simple in this case. And of course, there are many different measures for the consistency measure, which we will see. We have a third one to the first two, which we already saw. So let's first, before we go on, have a small demo. This is the set of generated points. These are 10 points, and it's not very complicated for us with our visual system to see that these 5 points here sit on a straight line, and this one and these 4 are outliers. So actually the data are generated the following way. So we produced a straight line, the true value for the straight line. Then we chose 5 points on this line randomly, and then we chose some 5 points in this unit square, -1 plus 1. So now let's look what happens if we do all the configurations. We see that the number of trials which we need for the complete search is 969. So this is 1024 minus those cases which we don't need to want to check. The number of trials which we specified implicitly for the Ransack is 17, which is significantly less. And now let's run the complete search. So it takes all these 969 cases and checks for the estimated variance factor and finds out that this line actually, which we have given, is actually hit quite nicely. Now we do the same with the Ransack, and we find out that the Ransack also finds this line. Now the difference between in the computing time here in milliseconds is 234 milliseconds, a fifth of a second, and here we only have 16 milliseconds. So you see that the pure reduction of the number of trials in the Ransack procedure leads to a highly increased efficiency of the result. So I repeat the same experiment once more, but we have a look at the individual steps in the Rundsack. So we start with the same situation. So we have the given points here. Here we see the different alternatives of Rundsack now, soon. Now we get the generated line. This is the line which is estimated from the complete search. And now we look what happens if we follow the Rundsack. So these are the 17 alternatives. And after 17 alternatives, it finds out, aha, this is the best solution of these alternatives. This was too quick to follow, so we make it even more slowly and follow the same situation once more. And now we can check for each individual case individually. So this is the first line which it uses. It's the first point and the fifth point, which is in this case this point and this point. And you see that all these points between 1 and 5, the first points are always the good ones, the last ones are always the bad ones. So these points are all sitting on the line. The residuals are small enough. So you see here the residuals being 0.0 whatever, 273, etc. So these are classified as inliers. The others are classified as outliers. So the second alternative is the fifth point and the second point. Makes no difference. Now we have this good point and this bad point, and obviously there is no consensus at all to the other points, which is to be expected. Same situation here. We have here 2 points which are very close to each other, which you might not see. So 1, 2 is here, and this is the outlier point, so it takes one of those, the first one, and this outlier point. Of course, the second point, which is very close to the first point, will be an inlier, so we get here a small residual of 0.009. Of course, the consensus is not very big because the number of points which confirm this line is only 3 here. So you see, this way we can go through, and we have here 3 case, we have here 3 case, we have here 2 case, only one inlier, one outlier. Same thing here. Now we have a situation which looks like to be good. So we have here the third point and the fifth point, but because the third point and the fifth point are a little bit off and the distance is not large, the line is a bit off, so it doesn't get enough consensus with the other good points. So you see that there is no guarantee, if we only have 17 samples, to hit all the possibilities. And of course we only get those solutions where 2 points define the line. In the previous case, with the complete search, we determined the line by line fitting through the inliers which we specified by the hypothesis. So this is certainly weaker, but the probability of getting a solution is very high. So this is the reason why this is worthwhile to have a look at in more detail. So we have these other cases which I just go through. So this was this demo. I will come back to this demo later. Now we are back from the demo, which we saw that it is quite useful to use this principle of Rundsack for finding lines in data which have a lot of outliers. So the principle to find a minimal set of points and then have a direct solution and have a certain number, quite small number of trials in order to have a guarantee that we have the solution with a minimal probability. Now I will talk about these 2 topics, the direct solution and the number of trials, in a little bit more detail. Direct solutions in generally may be hard to find. In the case of 2D line, of course, it's very simple. But imagine you have a point cloud and you want to detect a cylinder. This is a straight line in 3D which is 4 parameters, and the radius, so it's 5 parameters. So you need 5 points to define such a cylinder as a minimum. And it's quite tricky to find a direct solution for a cylinder through 5 points. In our case of a similarity from 3 points, things are quite easy, and this is shown on this slide. So imagine you have here the given 3 points, 1, 2, 3, in the given coordinate system, and you have here the 3 points, the corresponding 3 points, 1, 2, 3 prime in the observed system. And what you want to know is the transformation between this triangle and this triangle, described by a similarity. So what we do is the following, at least in memory. We shift this point 1 to the origin. Then we have the 2 triangles at this place and this place. And then we rotate this triangle into this triangle using these 2 directions. So in principle, we need to determine the scale difference between those. That is just the ratio of the lengths and the rotation from 2 directions with the methods which we discussed previously. Of course, we don't have to do the shift as such. We just take the difference between the coordinates 2 and 3 and 1 in the original and in the transformed system, and use these vectors for determining the rotation. As soon as we have the scale difference and the rotation with respect to x1 for the points 2 and 3, we know that the scale and the rotation stays, and we just rewrite this equation and solve it for xi prime in this classical form. And we see that the lambda r is just taken from here, and the translation is just this vector, which we remember we have seen several times when we solved the similarity. So the direct solution for a similarity from 3 points is quite simple. And the question is now, how many trials do we need in order to have a certain guarantee that we have a high probability to get a good solution? And there's the result, which I immediately will then prove. The minimum number of trials such that the probability of finding at least one good set of S points or 3 points is at least the probability P minimum. So the probability should be larger than, let's say, 99%. We have 3 points and we have an outlier right of epsilon. Then this equations gives us the minimum number of trials. These brackets are saying this is the ceiling of this real number, so we get an integer for the number of trials. If we have a look at this equation, this is if P min is fixed, 99 or 99%. The outlier right is epsilon, and the number of trials is S. So we see that we can have here logarithm of 1 minus this expression. So this is approximately t is proportional to 1 minus epsilon power minus S. That means the complexity of this method is approximately k power s. That means it goes with the power of this sets which we need. So we use the following equation. The probability of finding at least a good triplet when the outlier rate is epsilon and we have t trials is this expression. So let's have a look at it. So let's start. The probability to draw one good point is of course 1 minus the epsilon. Epsilon is the error rate, so 1 minus epsilon is the rate of finding a good point if you have one trial. Now we want to have s good points, let's say 3. Then of course this holds for each point. So the probability of having 3 good points or s good points is 1 minus epsilon power s. So it's the product of these probabilities. Now, then we have a good sample. Now, what is the probability to have a bad sample? That's just 1 minus this expression. So at least one of these 3 points is a bad point with that probability. Now this is one trial of 3 points. Now let's repeat this t times. So we just have to take this expression power t, so we get the probability to draw only bad samples in t trials, so we get this expression. And of course we would have at least one good sample, so we take the 1 minus this expression, so we get the probability to draw at least one good sample of size s in t trials. If the error rate is epsilon, this is this probability. And if we now invert this equation and solve it for t, we exactly get that what we saw here just before. That is this equation. So from this result we solve for t, so we take 1 minus p is this expression power t, so we have to take the logarithm of both sides, so we get the ratio here which is shown here. So let's have a look at an example. Here in this table you see the number of trials, the minimum number of trials as a function of the sample size, 3 in our case, epsilon, the outlier ratio, and the required minimum probability for getting a solution. We fix this probability for this table to be 99%, and we see here for sample sizes of 1 to 8, and for outlier ratios between 10 and 90% of the data, the required minimum number of trials. So they are quite small on the left side and very large on the right side, so this is certainly something which we would not like to apply. Let's start with an example. We start with this 17 here. It relates to the case where the minimum sample which we have to draw is 2. So this is the case of the straight line fitting where we selected 2 points. And we assume that the outlier ratio of the data is 50%, and then this table tells us it's 17. So why is this plausible? Now, what is the probability of selecting 2 good points? If the outlier ratio is 50%, so the first point is 50%, a half, the second is also a half, so the probability of getting a good point is a quarter. So if we take 4 samples, it will not be sufficient. If we take the double, maybe not. And this table suggests from our theory that we should take about 4 times 1 over this probability. So we need these 17 samples, which we have seen in the demo. This is the reason why we had there this 17. Now let's go to the second case. For the 3D similarity, there we need 3 points. And in case of an outlier ratio of 50%, we have to take at least 35 trials. So, okay. We see this is about double that from the case with a 2 sample. And we see that in this column, the ratio between consecutive numbers is approximately 2, which shows that the number of trials approximately increases with the 2 power the number of points in our sample. The same holds if we go to a very high outlier ratio, which we have seen that it works in this small example with a straight line fitting. Of course, we have here larger numbers because it's less likely that we hit a good tuple or triple, so we need much more trials. So you see here in the case of 3 points, we need about 4,600 trials in contrast to these 35. Again, we have here ratios of a factor 10 approximately, which is 1 over 1 minus 0.9, the probability of the outlier ratio. So we generally identify this behavior of the number of trials, and we see that for larger number of samples which we have to draw, the number of trials which are necessary to get a solution with a high probability is increasing rapidly. So here with 50% outlier range, we already need to draw about 1,000 samples. With 12, we would have about 2 power 4 more, so it would be in the range of 15,000. So this already will be quite large. That means we are not able to use Rundsack for cases where the number of samples which we have to draw from our points is too large. It should be small, let's say 10 or maximum 12 or something like this. What we also observe that these numbers are independent on the number of observations. That means whether we have a case with 20 points or a case with 200 or one with 2,000 points, the number of trials is the same, because we only talk about the error rate, not about the number of outliers. That means this method is obviously very well suited for cases where we have a lot of observations, which shows a big difference to the complete search, where the number of trials increases exponentially with the number of observations, not with the number of minimum points which we need for a direct solution. So let's go back to the demo once more. So let's do the following. We first have a look what happens if we take 12 points. Same situation, and let's have a look. So we have 12 points here. The outlier rate is still 50%, so we have 6 points here on the straight line, and we have 6 outliers. And now we see that the number of alternatives the complete search needs to track through is about 4,000. Rundsack still works with 17 trials. So the computing time for Rundsack will be significantly faster than the complete search, or better, the other way around. The complete search will take quite long. So let's look how long the complete search takes. It's about 900 milliseconds. Nearly 1 second is required to determine this line if you do complete search. If I do the same thing for the Rundsack, we have here, it comes out with 0, probably by some rounding. Let's try once more. So here we again have the 16 milliseconds, and here we have the 900 milliseconds. So the ratio in computing time is extremely different. Now let's go and make it even worse. And we go up to 14, which doesn't seem a big difference. But this means that the number of alternatives in the complete search is 16,000. For Rundsack is of course still 17. And it takes now, for the complete search, it's about 4 seconds. Here you have the 4 seconds, 4,000 milliseconds. And the Rundsack should still only need a few. So the Rundsack significantly outperforms the complete search, so don't do complete search. And of course, if you have, I made a loop, a condition in the program that if the number of points is larger than 14, I don't initiate the complete search because it just takes too long. So now let's take the situation and work with 50 points. 50 points. So now let's have a situation where we have 50 points. Of course, for our visual system, it's very clear where the straight line is. So the straight line is here, of course, and the Rundsack takes how many seconds? 0, so I have to do it once more. So it takes about 31 milliseconds, which is very fast. So let's do it once more. Oh, no problem. So now let's assume we have more outliers than 50%. So let's assume we have 70%. So what happens? Aha, the number of outliers is increased, the number of inliers is decreased, we still have 50 points. The true line sits here, and the Ransack actually takes, of course, 30 milliseconds, has no problem in finding this. Let's try once more. So, no difference. So let's start with, go to 90%. 90% means when we have 50 points, we have 5 inliers and 45 outliers. So where's the line? That's it. It looks difficult. So here's the line. Okay, seems plausible, but there are only 5 points on this line. And if we estimate, use Ransack, it's not possible for Ransack to find the correct line, which shows that Ransack cannot be perfect. If we would have done complete search, it's probably that it would have found it. Now, what can we do in this case that it still solves it? So let's try to increase the required probability. That means we have, instead of 99%, we have 99.9%. That means instead of 459, now we have 688, which is a little bit larger. So let's see what happens. Not much better. So it's obviously clear that if we have a straight line with random points on it and they are disturbed by random errors, then it's very likely that among the other 45 incorrect points, there is a configuration which mimics a straight line up to that accuracy. So let's try what happens if we diminish the standard deviation of our observations. That means we say the observations are much better, we generate them this way and we use this. But then it's not so likely that other points among these 45 mimic a straight line with that accuracy. So let's do the following. We decrease the standard deviation from 1% to 1 per mil, thousandths of this unit square. So we have practically the same situation. We don't see the difference. And this is the given line. And Ransack is able to find it. So the likelihood of finding a line correctly, of course, depends on how inaccurate our observations are. If the observations are very inaccurate, it's likely that the others mimic. If it is very small, it's not so likely that the others mimic a good result. We can go up to 95%, but then it's unlikely that we get a good result. No possibility. So we have to increase, let's say, the number of points, let's say to 500. Then we have the following situation. We see the line nearly, yeah? So the good line is here. And the estimated line is exactly at that point, and it took 1/5 of a second to find it. So this shows that in that situation where the outliers are not coherent in some way, but randomly distributed, Ransack is able to find a solution even if the outlier range is much larger than 50%. Here in this case, 95%. So this is very interesting to see. And the theory for the probability which I showed you doesn't take into account the uncertainty of the given points. So there is a lack in theory still open. So let's go back to the slides. So The theory and the examples which I showed you have quite some interesting properties. The first one, which I already mentioned, is that the number of trials which we need for finding a good solution is independent on the number of points. So we need these 17 samples independent whether we have 10, 100 or 1,000 points. This is a big advantage in terms of computational efficiency, because we can work with a lot of data which is not clear from the beginning. The second is, which is a minor thing but is essential, the sample size, S3 in our case, is usually smaller than the number of parameters. Of course not larger. So in this case we only need 3 samples compared with the 7 parameters, because each sample gives us 3 constraints on the results. The bad thing is that the number of necessary trials increases quickly with the number of parameters. And it increases quickly with the probability approaching 1. So if we increase the required probability or the number of parameters, things slow down. That means this method is really only useful for small problems, let's say below a dozen. There are still a lot of practical problems which have this property. One thing is, which I already mentioned, the result is only reachable with a limit probability. So we have no guarantee that we get a result. So if you want to implement that in a working system, you have to be to take into account that this is the case and have some backup if you don't get a result with that method. And if you ask what is the quality of the result, it's very difficult to evaluate, because it's a mixture of this estimation of the line, which is fine, or the similarity, but also the number of outliers and the distribution of the outliers. So it's very difficult to evaluate the result in a rigorous way. So there's no theory for the evaluation for the Runsack procedure. So we saw a concrete realization. Of course, there may be modifications, and there have been made a lot of proposals to improve the results in terms of efficiency or flexibility. The first one is, we said that we need to know the observational noise, because we use it for checking. Now, if we don't know it, we could say, aha, we take the smallest variance factor, assuming some standard deviation for the data at the beginning, the smallest variance factor up to that current trial. So if we do all the trials, one after the other, we could estimate the variance factor and take the best one of the trials up to now. The second is, we usually take all the observations the same. But after some time, after some trials, we might observe that some of these observations appear more often in the set of good observations. So we would like to use the sampling and take this into account. That means we take these points more often than the other points. The third one is, we said the consensus is determined using all observations at once. If there are many observations, it might be useful to say, let's try with the first 10, with the next 10, with the next 10. And as soon as we are sure it's a good or a bad example, we stop. That means we can do the consensus determination faster than if we take all the data, which is a very interesting technique. We could also, of course, at the beginning, eliminate bad configuration. So if you have a straight line fitting, you say if the points are too close to each other, then I don't determine the line. But of course this means you need to have some pre-knowledge about how the distribution of the points are, in meters, in millimeters, in pixels, or whatever. And of course, you could also say, if you have some prior knowledge about the solution, you could exclude those solutions from the beginning before you do the consensus, which are too far from this prior information. There's an interesting paper which I refer to, which collects all these options and also describes a unified framework for the RANSAC. There are a lot of applications, not only that one which we had in mind with straight line fitting or similarity transformation. It's generally the estimation of highly perturbed data, of course, for cases where the number of parameters is not so large. So we could estimate transformations, motions, similarities, affinities, perspective relations, etc. We could also use RANSAC for estimating geometric entities. So 2D line, which we saw already, we may use it for 3D line fitting or for plane fitting in 3D. If you have a point cloud, you want to find the planes. You might have want to find circles in the plane. In the brackets, you always see the number of the sample size, so you need 3 points for finding a circle, or if you have an ellipse in the 2D, you need 5 points. You might find spheres or cylinders in 3D. You could also ask whether you can find algebraic surfaces or curves. In general case, there you need some more samples, but these are still then curves or surfaces which only depend of, let's say, a handful or below a dozen parameters. There you can use RANSAC for detecting these geometric entities in your data. And you even could say, what happens if there are 2 lines in the data? Okay, you start RANSAC, find one of the 2 lines, which fits better, then you eliminate all those points and then repeat RANSAC on the rest. And then you can find a second or third line. So you can also find multiple transformations or entities in data using this technique. Okay, so far what I showed you is at the beginning we discussed what are outliers and what are the problems when we want to find outliers. I showed you a deterministic and a stochastic algorithm. Especially I showed you RANSAC, random sample consensus, which is a very efficient method for finding outliers, which is, so to say, the method which you use first. The complexity is exponential in the minimum sample size. And of course, there are certain limitations. So the number of parameters should be small. And we know that there is no guarantee for a solution. And if you can live with both, then RANSAC is the choice. Of course, there are other algorithms which work very nicely if the number of outliers is small, the percentage of outliers, let's say 1% or even lower, and there are only medium outliers or small outliers. Then these algorithms only have a complexity of the number of parameters power 3, which is only polynomial. And that means you can use these algorithms for very large U, let's say U equals 1,000 or 10,000, and still have an outlier detection routine. And you can imagine that these estimators can be a modification of what I showed you on slide 21. So, what is the strategy behind what I told you, these lectures? We start at the end. We first find the outliers with some adequate methods, in this case probably RANSAC, and then afterwards we take the inliers and perform a maximum likelihood estimation with the inliers where we assume that they are Gaussian distributed. We have a nonlinear problem in general, but we are able to perform a rigorous evaluation with all the tools which we discussed. That means at the end we come up with a solution where we understand what the estimation actually did, namely using the inliers, performing a maximum likely estimation, and the evaluation is with that semantics which we discussed in the lectures. So, This closes the lecture series. I thank you for watching, and have a look at the slides. I will prepare the references soon. Thank you very much.